Okay, so we're moving into the topic of isomers, all right? And isomers are any compounds that have the exact same chemical formula but have different structural formulas. All right, so classic example of this would be if I were to ask you to draw a compound for this formula right here, C2H6O. All right, and if you did it, if I just asked 30 people to do this, a lot of them would probably come up with this structure right here, but some of them might come up with this structure right here. It's not that anybody's right or wrong, it's just that there happens to be two different ways that you can connect these numbers of atoms to make a totally correct structure. All right, so these are actually two compounds that exist. They happen to have the exact same structure. All right, so one thing about doing organic chemistry is that you'll notice that there's a lot less reliance on using formulas and a lot more reliance on using structures, because when you're doing, if I say NaCl, sodium chloride, or H2SO4, there's no question about what the molecule is that we're talking about. But since there's the ways to draw things in different ways from the same formula, you really have to start to get used to drawing structures in organic chemistry. All right, so there's a lot of different types of isomers. We're probably going to spend more time on some versus the other, but it can be broken up this way. Isomers can be broken up into what are considered stereoisomers and structural isomers. All right, stereoisomers can be further broken down into configurational and conformational. And configurational can be cis trans EZ versus optical. And I know that these words don't have much meaning right now, but we will talk about what they mean right now. So first of all, before we start talking about what these things are, I want to point out something that's important to know when you're looking at isomers, which is you need to be able to tell the difference in whether two things are the same or are they different. All right, and there's a couple things. So for example, if I were to show you this and this, all right, are these two molecules different or are they the exact same thing? All right, well, I mean, there's some obvious differences about it. These guys look kind of, this looks like it's kind of curled around on itself, whereas this thing looks kind of like it's a straight line. But in reality, these are just the exact same molecule. All right, and the reason for that is, yeah, if you just there's a couple things. If you just flip something over or rotate it, you don't change what it is. All right. Also, if you rotate it, certain bonds can be rotated around, and just because you rotate around a bond, it's like moving your hand from one position to the other. It doesn't change who you are. Right? It's just your limbs are in a slightly different direction than they were before. All right. So the other issue that we can have, so three issues that we can have. First of all, is that when you have tetrahedral geometries, all right, they have a three-dimensional shape, and one of the ways that we do this, the way it's typically done, is you use these wedges and these slashes. So anytime it's a solid line, it's assumed to be in the plane of the paper that it's written on. When you use a solid wedge, it's coming out to the front. All right, this is going out to the back. All right, and so these three would be like the legs of a tripod. All right, so what I want to ask you, and I've actually already given the answers here, but if I drew these, and I'm just using A, B, C, D as just a way of labeling. So FYI, this C in the middle literally stands for a carbon, but this C just means group C. All right, so if I were to show you these two things right here, would these be the same molecule or would they be different molecules? All right, well, as it turns out, these are the exact same molecule. All right, and you might be thinking, whoa, wait a minute, this one's got an A on top, but this has got a D on top, and this has got the A is down here. Well, here's a way to think about this. All right, notice that the B in both of these cases is in the exact same case. Sorry, in the exact same place. All right, so what I want you to do is think about this bond right here as being like the axle to a steering wheel. All right, so this would be like the column of the steering wheel, and we're going to have a steering wheel where we have three letters on the steering wheel: A, C, and D. All right, so you can kind of think about the steering wheel as coming out towards A, and it's going to go down, and it's going to hit C, and then it's going to start to go back away from you. This is the bottom part of the steering wheel. It's going to hit D, and then it's going to start. So right now the steering wheel is behind the plane of the paper, and it's going to eventually come back up to the 12 o'clock position at A. All right. So what I want you to do is think about grabbing that steering wheel, and I want you to rotate it 120 degrees to the left. All right. Well, if we rotate that steering wheel, we're going to rotate it this way. Well, what's going to happen is A, so essentially what we're doing is the steering column stays in the same place. All right, we're rotating around that steering column. A is going to move to this position. That's what it did. C is going to move to this position. That's what it did. And D is going to move to this position here. All right, so these two guys are the exact same molecule. You're just looking at them from a slightly different. Actually, what we've done here is we've rotated around a bond. All right, but that doesn't change what the molecule is. All right, but what if I were to say this versus this? All right, well, at first you might think, well, again, your gut instinct is they're not the same. All right, and in this case, they actually are not the same. All right, so notice here, B and A are in the exact same place for both of these. All right, what's different is that C and D have switched positions. All right. If you made a model of these two things, there's no way that this would be the exact same thing as this. All right. And we'll make some models in the next video to show better examples of this. All right. And I probably should have shown this one first because I assumed that you knew it here, is that single bonds allow free rotation, but double bonds and triple bonds don't. All right. So if I were to show this molecule right here, and this is a single bond right here, and since it's a single bond, we could rotate around that just like it's an axle. And if we rotated 180 degrees around this bond right here, that's going to flip this thing from the downside to the upside. All right, so these two guys would actually be the same. All right, but if I draw this molecule right here, this is a double bond. Double bonds do not allow rotation around them. All right, so if we've got this orientation around this, okay, and remember this is a line angle structure, so there would be a hydrogen coming up here and a hydrogen coming up here. This is not the same as this. All right, you can't just rotate around this bond because it's a double bond, so these would actually be different compounds. All right, the last thing to keep in mind is that if you could just rotate or flip a molecule around and it becomes something else, it's still the same molecule. All right. So for example, if I take this molecule right here and I just rotate it 180 degrees, or sorry, that would be 90 degrees to the left. All right. This becomes this. All right. But what if I take it and let's pretend this is a pancake, and I put my spatula under it and I flip it over to the left. All right. So if you flip it upside down, that is going to basically create a mirror image of this guy, and it's going to be like this. All right. But just because you rotate or flip something doesn't mean it's different. All right. And the last thing I'll do is, what would happen if we're combining this rule right here. What if we rotated around this bond right here by 180 degrees? All right. Well, since that's a single bond, we can do that. So this right here would make this. So notice that these are all, I mean, they're slightly drawn different ways, but they're all the exact same thing. So one thing is you're just going to have to get and it comes with practice. You'll be able to recognize whether two things are the same or if they're different, even if they're slightly drawn different ways. All right. So the first type of isomer that we want to talk about is a structural isomer. And a structural isomer is one that results from atoms physically being connected in different orders. All right. So if I showed these two molecules right here, all right, notice this has got a 1, 2, 3, 4, 5 carbon chain, and this has got a 1, 2. The longest straight chain on this is only 4 carbons long. All right, literally. But if you count up all the carbons and hydrogens, and you find out they have the exact same formula. All right. So one way to notice a structural isomer is that in order to make one into the other, you would physically have to disconnect one of the atoms and reconnect it to a different atom. All right, so if we pulled off this carbon right here and we attached it right here, we'd make this guy. All right. So by contrast, there's also what are called stereoisomers. And here, atoms are connected to the same atoms. It's just the direction that they come from the atom that's different. All right. So, for example, if I compare these two molecules right here, and I've labeled the carbons A, B, and C. All right. So you can see A, B, C, A, B, C. That part of the molecule is exactly the same. But one thing you'll notice is that this next guy comes down, whereas this methyl on this one goes up. All right. So in this case, these are not the same molecule. I mean, they would have literally different physical characteristics and chemical characteristics. All right. So the thing is though that they have the exact same groups attached to the same atoms. All right. If you look at this, to B, we've got a methyl group. All right. Same thing over here. To C over here, we've got a methyl group. To C over here, we've got a methyl group. All right. So to get from one to the other, even though you can't rotate around it, the difference has to do with the direction, not the actual atom that it's bonded to. All right. Another example would be something like this. All right. So this shows a molecule, and we've got this. We know that since this is a tetrahedral carbon, we have 4 groups that are coming off. And what I've shown is this one methyl group coming towards you. All right. And one thing when you draw this that a lot of times isn't drawn is, well, isn't there one more group? I only see 1, 2, 3 things coming off that carbon. Well, there's one more hydrogen. All right. That's just not drawn. And you'll get used to that. If I drew a hash mark going back in this direction, there would be a hydrogen drawn there. All right. So why did I not draw that? Because I'm drawing it as a line angle structure, and we don't have to draw hydrogens off of carbons. All right. But what if I compared that to this, where this shows something going back? That would be assumed to be a carbon right there. All right. So are these the same or are they different? All right. These would actually be 2 different molecules. All right. These would be considered what are called optical isomers. All right. The difference is that it's not what is connected to what atom. It's the direction that things come from that atom. All right. Here, to turn this guy into this guy, basically the carbon here and the hydrogen going back would have to switch places. All right. So that is a little introduction to isomers. There are more types of isomers, and we will talk about them in the next video.